Hi, I'm Tom and I talk about code. Welcome to another Rust programming livestream. Today we're doing more work on my compiler for my own programming language, compiling for a virtual machine that I have also built and designed, my own bizarre instruction set architecture. Today we have one problem. We're trying to optimize my compiler at the moment to be smarter and to use registers instead of doing a lot of stack manipulation, and in doing so, trying to be smarter about it with broken function calls. Now actually, there's kind of like a zero thing here, which I won't bore you with writing right now, but I just remembered I had a conversation with a friend last night about some of the problems I've been facing, and one of the main problems I've been facing is this idea that sometimes I need a reserve, sometimes I need two temporaries to shuffle things around while I'm working, right? Two temporary registers, two registers that are just intermediate, that have no persistent state, right? Because sometimes we're doing some math and we need to pop two things into them. Anyway, I had this realization. Well, that's not true. My friend had this realization. This is arithmetic. If it's a pointer, T1 comes from, yeah, so we do this multiplication, right? This multiplication comes up, and this is one of the places where we need to use two temporary registers because we're shuffling things around. We do this multiplication when we're adding a number to a pointer, for example. And I've written this out lots of times before, so I won't belabor the point too much, but just to demonstrate, because I think it is always interesting, we have an integer a, and we say a plus 2. What is a plus 2? Right? Is it the address of a, the address of the thing we're pointing to plus 2 bytes? Or is it plus 2 times size of int? And according to C logic, it's 2 times size of int. So we do this multiplication. But my friend was like, hold on. Why are you multiplying, right? Especially if you're, in this case, you could do this without a multiply instruction. You know this ahead of time. And I was like, huh. Now, it doesn't work. It could be a variable. It could be a variable, but that would kind of. So if we only add constants to pointers, then we could do away with one of these multipliers. I thought that was a really interesting point, and it definitely would save a really cumbersome instruction and a bit of juggling. So this is a fun optimization that I should keep in mind somewhere, but also we don't actually know. When we pop this here, we don't know if this was a literal or if it was a variable. So the kind of logic I would need to do that would be a little bit complicated. At this point, the expressions on the left-hand side and right-hand side have already been compiled. So I actually think this is a non-starter, but I think it was an interesting idea that I'm doing this multiply, and he was like, don't you know the size of the thing if you're doing a plus 2? And I was like, yeah, I do actually. I could pre-calculate that. I could do that all up front. But we do still need a runtime multiply. So interesting thought. And it would be nice to omit instructions that are pointless, right? To just have one instruction instead of two. That would be a much smarter optimizing compiler. But I don't think that's something we need to necessarily get stuck in today. The problem is, my machine only has 4 general purpose registers, which is not a lot. So it turns out that juggling things between 3 general purpose registers was hard. So I've actually mulched my page register and made it another temporary. And we're going to deal with the implications of that down the road. Maybe what I really need to do is go into my ops and really think about how many of these things I need, because I've only got, not too many. Like maybe I could do this with, maybe I could steal a bit from here and put it into my registers and double my number of registers, maybe. But yeah, so I'm having some problems. In conclusion. But I worked out a middle ground. If I sacrifice the page register, and we'll deal with the implications of that later, and in my function call, I decided, because all my functions return in the A register, so I'm like, okay, when we call a function, we push the A register first, and then we try and restore it afterwards, and end up with the thing that we evaluated on top of the stack. That's a thought, right? That's an idea. That's a big idea. And the problem is, when I run my tests, it breaks. And that's not good, right? Bugs are not good. It's not good when your program doesn't have the expected output. And what's even weirder is, this doesn't have the expected output in a test designed for inline assembly, which is not a Ah. Inline assembly kind of is a function, but also kind of isn't, right? Because my inline assembly, if I look at top level, inline ASM, it actually makes a function definition. So maybe this isn't actually surprising that this breaks when I start meddling with my functions. Because, the way this works is, when we compile a function definition, we compile a list of statements, and that's fine. And we work out how many locals we have, and we do some little fiddly stuff. And then when we compile a block of inline assembly, we actually compile it like it's a standalone binary, and we grab the bytes out of that section, which is good. Which is good. I'm trying to press into C. This is all okay. This is all okay. So this is actually fine. This is actually fine. I think what I need to really do is this really jank thing where I have this file that I compiled from, and we're going to load this test. We're going to load this test here, and I'm just going to step through the actual instructions in my little virtual machine simulator. Cool. So we can dump, if we encode our final binary as base64, we can actually dump it into the browser really easily, which is cool, So let's load up Firefox. 5713, I think, 5173. I can never remember this port for Vite. That's the one. Cool, so bin equals this. And that didn't work. What did I do? What have I broken? Oh, I didn't actually give it an input file. Excellent, that makes a lot more sense. Okay, now we have a binary viewer, and I can zoom in here. So we can step through this. It's not that many instructions. So let's see if we can work out. So what's the problem again? The problem is I'm expecting 14 and I get 18, or expecting 18 and I get 14. 7. I should get 18 and instead I get 14, which is a bit weird, So, I've got thoughts already. But we'll see. It would be very interesting. Right, it says it's reusing variable B in register C, and that's not correct. That can't be correct, because register C should be a temporary, right? When does this stop being a temporary? Update var in register. So, okay. I don't know why this is suddenly different, but update set variable register. If this is a temporary, it should do nothing, right? We don't remember, we can put a variable in there and use it later, but we don't remember it in a persistent way. Now maybe this is a problem. Now maybe this is a problem, but it shouldn't be, right? And what that means is we should never actually end up in this state. So something is inserting. Now I wrote an insert directly, I think. So if registers insert, that's fine. This is where I did it. Register, we're setting register A. So that's the one I wrote, and that's okay. If it's a temporary, we don't do anything. If it's a free, if it's anything else, we set it to free. That sounds good. Here, if it's free, if it's a literal, if it's a temporary, we shouldn't do anything. So that's okay. Cogen block. Did I do something weird here? No. So when does this get set? When does this become... when does this think that register C has state that it should not have? When does this happen? It's here. So it's when we compile the expression A. We end up here. We're using A and A. So what expression... It's the one, it is literally this assembly, somehow. What? When we call this function, we end up with doing something with the C register? What? we compile this, add nums A11. So that's okay. So we call this, and then we return compile expression 11. Yep. Expression, compile expression A, that's fine. But where is, oops. So it should be B equals this. B equals this. So it's when we do this assignment, somehow we end up, what's going on here? Where are we? What's going, where do we have it? This is hard to read because it wraps. So this int B equals. So we do this expression. And we already have A in a register, which is great, so we don't need to do extra work. And then here, where does this come from? CodeGen block, update var B in register C. Update var B in register C. But when we do that, CodeGen block, my mistake. Update variable register. This update var name register C. This is what we're seeing. Update var B register C. And we do this through, like, we call get variable register, set variable register. So this should be fine. Because we just checked set variable register doesn't do anything crazy. This respects the temporary. It just does. It just doesn't do anything. So let's put another trace log, right? Because this is how this stuff is useful. Set variable we'll say try set, and then if it's temporary, we'll say trace really bad logs, but that's okay. And then I'm going to rerun the compiler, and we're going to get a little bit more information about what's going on here. Try set in register C. So let's just log the entire self. Let's log the entire state when we see this, because that's going to be more useful. So when we do this, C is free. C turned into a free somewhere. Where did that happen? That's not good. That's really not good. Free. Yeah, that's not good, is it? That's really not good. Invalidate. If it's not a temporary, we do that. Get a free. Clear intermediates. Intermediate gets set to free. That's okay, I think. Unless it goes intermediate to free. That's also an option. Set variable register. That's fine. Set temp. So we've been here, so this is fine. What about places where we ignore this, right? So when we do this set for the A register, that makes me nervous, but not like super nervous. Set intermediate. Ooh, okay, so let's say if R is register C. Right, let me just, because this has to be the path. This has to be the path. Trace, it has to go through here. It just has to. Be in register C. Trace. Maybe not. But we end up with it as a free somehow, which is not right. It's just not right. Now, intermediate. Temps should not be intermediate. But these things should be... We'll leave that for now. We'll leave that for now. If it's intermediate, then it becomes a free. Like, this just feels really sus to me. You know, this feels very, very suspicious. Very, very strange. Very unusual. Okay, but it's good. I feel like we're closing in on something here, which is nice. Free return and register. That's fine. Because like this feels a little strange to me as well. Set temp. That's probably okay. Oh, actually, hold on. Yeah, it's, well, everywhere we call... We never want to call reserve... Look, I'm just going to hack this into the function call to, like, do nothing. Because we don't need to anymore. And does this now... This should now respect this. We actually have a code path that was unsetting this. I got a bit confused. So now if I make t, at the very least that should be correct, I think. No, it's still wrong somehow. Huh. But... I mean, we never think we have something in a temp register, which is good. That's really good. Okay, so we're going to grab this now, because the final binary should be a little bit different. It's the same length, which is good. So let's see what happens. We set up two locals, because this is how locals work. We have two locals, A and B. So A is going to get 7 loaded into it, which is good. We store it in our local. Fantastic. Now we're going to load 11. Which is the first argument for add nums. It's actually the last argument, but we do them backwards because stack. And that gets pushed. We then push A to the stack because this is our second argument. We then have to push A again because this is the thing we're going to restore from. And this now has broken our function call. That would explain it. So actually, we need to push A before we push any args, right? Because... But then we need to know how many args we pushed so we can pop them off. That's annoying. That's really annoying. We can do it. We can do it. It's just annoying. So this has now become the first argument to the function, which is incorrect. So we're adding 7 to 7, which is 11, which is 14. Sorry, which explains why we're not doing 7 plus 11 and getting 18. That makes sense. That makes a lot of sense. That makes a lot of sense. Okay, so let's do it. Let's do it. Let's fix this. Let's leave this in this state for now. So what do I need to do when I call a function? I don't know how I didn't notice this. Call a function. This needs to come earlier. So if we're gonna push A, we have to do it like back here. We have to do it before we compile any of our args. For arg and args, so we need to say out. We need to do this. We need to say out.push, push A to the stack, then do all our args, and then when we return, we can't just pop, we have to update the stack pointer. We have to, so we've got the stack pointer. We need, before we do this, and this in general is probably good advice, right? Because we remember where the stack pointer is after we've loaded all our args. In general, we probably want to just like would shift the stack so that we forget those args are there, because if we push something to the stack before that, you know, we don't want to have to sift through all of our args. We don't want to have to know about that. So before we do this, before we push A, right? So we've done our jump. We're going to jump back to here. The first thing we want to do is probably load an immediate into C, because C's been mulched by our function call. And that's okay. C is special in the context of function calls. We are allowed to hard code it. What we're going to do, this is why C is our temp register, because of how it gets treated around function calls. What we're going to do is we're going to work out the number of args. So let's do that up here. Let's say, oh, we have args.len. So we'll load imsigned, add imsigned. So we can add assigned immediate to, we can actually just do this to our stack pointer directly, and we want a literal 7-bit and we want from signed. Perfect. -1 times args.len, and I think that's beautiful. So we're just going to subtract a bit, except we need to multiply this by 2 as well. Oh, is this going to get too big? How many args would we be allowed to have? It's a 7-bit number. That's fine, that's fine. So it would just be, I don't know, we'd be allowed to have like 60 args before this broke. That would be okay. We can have up to, 127, right? That's the biggest negative number we can represent. So args is just passed here. That's okay. And we probably need to tell Rust that this is a U8, and we're going to do with it being a U8. It's actually -2 times args.len, which, sure, that sounds good. And we're just going to say as U8, as I8 even, signed. Sign is important. Cool, so now we've shifted the stack back. We actually haven't touched C again. We push the result, we swap it, and then we pop the thing that was previously in A, and so we end up with the result of the function call on top of the stack and the other thing underneath. And I did this wrong because this is just an instruction. There's no unresolved part here. And apparently I can't do brackets because I added a bracket. You need to also close it again. Add imsigned. Just have to add a nice little unwrap. Alright, so args.len has to be as U8. We need to just shift where this bracketing happens. That is all good. I8 rather. I keep saying U8 when I mean I8. That's not good. They're quite different types. Okay, I think I have an unnecessary set of brackets. That's what I want. Okay, that took some thinking, but that's okay. And it looks like, well, it looks like more stuff passed, so that's really good. That's really, really good. Inline ASM is now okay. We're passing stuff correctly. This makes me happy. It's always array instruct. This is always the thing that fails. This has failed so many times for so many different reasons. But that's good. We've got different errors, okay? If we're gonna have errors, they may as well change over time. That feels like some kind of progress. I keep saying this, right? But it feels like progress. Okay. So, let's pull up our struct test. It's an array test, isn't it? Sorry, array instruct. We're going to load this back into our file. We're going to load this into the VM. We're going to see if we can work out where this blows up. Cool. We're going to grab this. What was that warning? Hold on. Whoa. Unreachable. Yeah, that's fine. That's okay. We have accepted that. So once this works, we're going to add that reserve back and see if that actually broke anything. But we'll go without it for now, because we don't need it anymore necessarily. We kind of do. It's kind of complicated. Programming's hard. So the problem with this code now is We're expecting 255 and we get 0. Why? Because we're putting hex FF at element 20. Okay, so what's gone wrong? What's gone wrong? What are we putting foo.bar.alum? So we're going to have to do a lot of clicking here. Okay, so we jump down to main. Right, this is all our main. There's a lot of main here. There's a lot of stuff going on. We're going to load this constant. We're going to shift left by 4. So this constant 4096 is now in A. We're going to store it as a global, which lives at address 0. Our first global lives at address 0. It feels very loosey-goosey, but I love it. I love it. We push A to the stack. Why do we push A to the stack? I'm not entirely sure. Oh, because it... mhead. Why do we push A to the stack? I don't know. I don't know what this is. I don't know what this is doing. I don't know where this came from. We're going to load 100. We're going to push that to the stack because... Oh, we push A to the stack because we're about to do a function call. And we want to restore A at the end of it. That's why. That's why. That makes sense. That makes sense. Okay, cool. So yeah, so in this case, it's really unnecessary. But it would be useful to maybe have some kind of control for this so that an expression could say, hey, I'm in a chain of expressions, I care about the A register, and then we know. Because we have this thing called, it's literally called state, right? So it would be nice to have some kind of more meaningful state passed around with it. State. Oh, at the moment it's just register state. We could have something like is in chain. And if this was true, it would mean, you know, we need to preserve the A register over function calls. If it was false, it would mean, like in this case, it's really redundant. We wouldn't need to do it. Anyway, that's a fun thought. Stick that one on the back of the brain. We're going to jump to a function. We're going to jump to a function that is going to... Our little malloc, that's very cute. We load our global variable, which is great. We're going to do some things. And this all looks okay. A lot of shifting here, a lot of back and forward. But we're going to end up with this magic number, the address we just allocated back in the A register, and that's what we want to see. Now, the stack should get reset. This makes me a little nervous. We should have pushed one thing to the stack, right? So we should subtract, you know, we have one argument, we should just move the stack back by 2, which should be fine. Should be fine. We push A to the stack, we swap, we pop. What was in the A register before? Something, right? It should have been this same value. So, okay, so we've corrupted the stack, basically. That's good to know. I'm surprised so many of my tests passed if I'm just blatantly corrupting the stack when I call a function. That almost makes me nervous. What would be really nice would be a stack viewer, a visualization here where we could be like, hey, what are the top n things on the stack? Because that'd certainly tell us what's going on. The other thing we can do is just reset the machine. Okay, because this sets up the stack pointer, you know, 16. Yeah, okay, so we're gonna, when we jump into this function, the stack is at 16372. Okay, 16372. 16372. Cool. We push the stack up by 4. Let's draw this. Let's draw this as we go. Okay, we're gonna go back and forward here. So, that was a really bad we'll say at main, my god, I can't write. At main sp equals 16372. Numbers are hard. Okay, so then we plus locals. And this gives us 16376. Cool. So then this is in A, we do some stuff, and we push PC, so we say, let's say PC, let's say at 70, at 72, push A, which is hex 1000, and we push it address well, we push it 16376, and the stack pointer goes to 16378. 16378. Excellent. Then we call a function. Okay, so we do some stuff after this. A lot of stuff happens. At some point, we're going to jump back here. Okay, so now we're at 86. We've returned, and our stack pointer is 16378, which is great. So we don't need to make note of that. After we subtract, we go back to 16376, which isn't right. Are we already factoring this in? We're off by 1, maybe? I'm interested. I'm interested to know. Maybe this is off by 1. Maybe we actually just don't need to do this. But the stack pointer we push and restore. Like, we push the stack pointer after we've pushed all the args. So this is the stack pointer we're going to restore, right? So let's maybe just do the silly thing that is probably correct. And subtract 1 from this thing. Minus 1. Let's, well, I guess we do this. Because if we don't put brackets around it, this will be minus 1 as I8, and then we can't subtract an I8 from a U size or something. We probably can subtract an I8 from a U size. Anyway. Oh no, we can't, because if the U size was 1 and the I8 was like negative 200. Anyway. Let's try this. Okay, now our soft multiply breaks, and I think this is an earlier test. It is. So, let me try the other thing, which is we just don't do anything. But that doesn't work either, because that's kind of what we did before, right? Okay, so let's go back to this. Let's go back to this. This thing that breaks. But let's look at our soft multiply test. And this is in tests. This is a good question. It's in lang tests functions. Lang tests. I don't know, I can't remember which file this test lives in. Lang tests. Is it just in compiler? Soft multiply, here it is, okay. So let's grab this, and let's see if we can work out what happens when we call this function. Right, what do we restore to when we call this function? Now we do it with 7 and 8. We're going to pick 2 smaller numbers so that I don't get RSI from clicking, and that's fine. That's probably good. It's probably a good idea. Okay, so yeah, let's see what happens when we compile this. What does this code look like? Soft multiply. So, you know, it's not that much code. Oh, I forgot. Hold on. I need to make these smaller numbers. Let's say 2 times 2. Okay. So this is still a lot of clicking. But that's okay. So we come down here. This is our main function. We do some stuff, we set it up, and we do our call. So our stack pointer is at 16382. Hold on, let me reset. Let me double check. So when we push A, okay, I clicked too much already. So we push A, which is nothing. That's 16374. Okay, 16374. 16374. We're going to remember this. 16374. Okay. So here we go. 16374. Still going to be a lot of clicking. This is loop 2. 16374. We're remembering 16374. Okay, should be... Oh no, here we go. We're done. 16374. What's our stack? Oh no, this is the end. So now we go back to 36. 16374. 16374. Weird. Okay, so that's actually what we expect. 1637. So the stack goes back to what it was here. Huh? Huh? BPSP. We push the base pointer, we push the program counter. Do we get the stack pointer back from the... Huh. Oh yeah, right, we get it back from the base pointer. That makes sense. That makes sense. So actually we don't want to subtract here. We want to go back to... Oh crap, this is like the opposite problem. This is like... Huh. Do I just never restore the stack properly? Wait. Oh god, do I just... Wait, am I misunderstanding something? Do I just never restore the... We add to the stack. Why do we subtract the stack pointer? SP, what is this? What have I missed? What have I forgotten? I'm obviously doing something here, right? But I've kind of forgotten what I'm doing. Anakim Luke, welcome. How you going this morning? You did say look, that's okay. No pressure to respond. System stack. We push. So the stack pointer. We set the base pointer to the... Oh, right. We set the base pointer to the stack pointer here. So then when we do this... Yeah, and then we add him signed. So when we return from a function, so at the end of a function, so this is in... this is in top level. We already do this subtraction, I think. Argslen as... Yep. We do this. Cool. Okay, so we do end up back where we were at the start. So this should actually work without the explicit manipulation I did. So this was fine. I don't need to do this subtraction. This was fine. I'm overcomplicating it. So let's see if we can do this. Let's see if this just works now. Let's just make T this. An array instruct. It's always array instruct. Alright, well that's interesting. So let's go back to array instruct. Okay, we should just be able to compile this, chuck it in binary. And so this is saying that we're at some point, we're trying to jump to... At some point we're trying to jump to 261, which feels an awful lot like the wrong thing. So again, this is stack corruption. This is tricky stack corruption. Zymus, you like my debug UI? Thank you so much. That's it was fun to build. This is an off-the-shelf library, by the way. I'm not this clever with CSS. This is called 98.css. Highly recommend looking at it if you want to do fun retro stuff. And it's like an old IBM BIOS font, which yeah. I need to polish this up just a little bit more and put it on my website, and then people can play with it, because I think this is a cute view. I also need to work out why there's two new lines here. I don't know where they come from. I don't know where they go, but they're there, and they're really annoying. So little polished things like that. Bear Zymus, how you going? You doing any fun PS2 stuff at the moment? Any cool and weird things being built? Sorry, I do just need to quickly check my phone. Cool. It was just making sure my plans for tonight are good. Today's a very special, very spiritual day in Australia, right? It's the day before the Australian Football League Grand Final, which I'm probably not going to watch. But it's a public holiday in Victoria, so that's really exciting. We literally get the day off because there's a big sporting event this weekend. Working on the 989 SND sound driver. What's that from? What's that used in? I don't know that driver off the top of my head. Okay. So, tons of games. Okay. Well, that's cool. That's really cool. I'm very fascinated by that kind of sound stuff. It's an area I haven't even. Okay, yeah, all the big players. It's an area I haven't gotten into, and as a music guy, you would think I would be all over that, but yeah, I've got to still look at it. All right. What has gone wrong here? What's going on? Why? How are we getting here? So at PC, we're jumping to 261 because we've corrupted our stack. I need a stack viewer. Oh. I need a stack viewer, or yeah, okay, let's build a stack viewer. Let's do it. Let's go. Let me bring up my correct terminal that you guys can all see. Web, learn simple VM. Okay, so we're gonna do some JavaScript real quick. What state is this in at the moment? Okay, yes, good. Cool. X11 motif style. Motif style. Is this really the chunky one? Like this kind of? I mean, this looks like not maybe that. Yeah. This very default X11 kind of look. It is pretty beautiful. So maybe I need to build this. Motif framework. This isn't it. This ain't it. I don't think. Hold on. No. Okay, cool. Well, yeah, that is a fun style. I do like this. I do like it. Okay, so what I'm gonna try and do is VM.view maybe. So we have this VM. We have our state that just gets dumped out into a pre. I'm probably just gonna add another pre. And this has been my approach, right? Just like get the basic flow working. Now, this is hard, right? Because I don't know if I want to write code. I don't know if I want to write a function that does it. I don't know if I want to try and because I could just reference a field and I could just update a field with the stack, like a list of the top 5 or 10 elements of the stack every time I do something. That would kind of work. Or I mean, the other thing is, I don't know if it's... Okay, no, let's just say, let's go... Let's maybe go div. Let's make it a div. And let's put a v4, and I can never remember how v4 works. So we need to double check because, you know, docs-driven development is good. v4, and I want a pre. Let's v4. Let's say frame in frames. And maybe we'll say something like frame. We'll do something like this, right? Now, vm.frames. So let's go into our VM and let's just add some like really dumb placeholder data for now. I think that probably makes the most sense. So vm.js, because I've got these weird wrappers, right? I've got the internal. It's silly. It's silly. Let's say this dot frames. So we'll add just some hard-coded data to start with, and I think that's a good way to just play around with it. So let's put a BP at 100. Let's say stack 1, 2, 3. That's not quite the list formatting that I want. That is not quite the list formatting that I want. So let's think about a different way we can format this. Frame.stack. Can I, hold on, JavaScript list join. Okay, so array, so I can just say like join. Maybe that's better. Cool. Okay, that looks nicer. That looks nicer. Not the most elegant layout I've ever done, but that is fine. Let's also like just lose this weird spacing because I just realized that respect white space like that. That's a bit better. That's a bit tighter, right? That's nice. That's nice. And now, I mean, honestly, like this can probably all just go on one line, right? Because we only have 8 registers. That's fine. That's pretty good. Okay, so the stack frame starting at 100 base pointer, we have a stack. This is good. This is good. Now we just need a function that actually calculates this. So let's add this. Let's add a function on this. We'll say calculate frames. Cool. So the first thing we want to do is we want to say let bp equals this.vm. We want to get the base pointer, and I'm pretty sure that's what, because yeah, .vm, yeah, this is our like this is our Rust type .vm, and then we have a JavaScript wrapper over it that gives us a nicer API. So that's cool. That's cool. Now we have a base pointer. We say while BP isn't 0, we're also going to say this.frames is empty list. So while the base pointer isn't 0, because the base pointer starts at 0, right? We're going to walk back through our frames until we find a base pointer that is 0, and that's when we're done. That's our terminal condition. So we're going to find... now we want to grab the stack pointer. So we have the base pointer. We want to start with the stack pointer at the current place. So this VM get register sp. Cool. And these are done with string names. This is a bit clunky, but you know, enums are hard. Enums are hard. I think this is fine. I think strings are fine. We can survive that. I just spilled tea on my face. Cool. Okay, so while the base pointer isn't 0, well, first off, yeah, okay, let's do it like this. Let's do it like this. So the stack grows up, which is really stupid. I don't know why I made this decision. I'm going to regret it. But anyway, the stack grows up. Yeah, like I should probably do something like that. Ideally, I would export it from Rust, and I would just have like some WASM. Like, I don't know if I can do that, but I don't want to have to keep things in sync necessarily, because I don't know if I'm going to have these names for my registers long term. Like, because my machine, like BP isn't really the base pointer, but I'm exporting from WASM, right? I don't know. I haven't worked out how to do this from WASM yet. So this isn't like a JavaScript export. This is a Rust export. Yeah. My virtual machine's in WASM. The registers are defined in WASM. And basically, I'm considering at some point just renaming my registers to R0 through R7, maybe. Or, you know, like R0 through R8. I don't know. R0 through R7. But like maybe, oh no, it's a 0 register, so it's kind of got a fun name anyway. Because the base pointer is only defined by how I use it. So yeah. So I just need to make a decision about how to do this. I need to work out how to do it, but I haven't done it yet, so I'm doing strings, which is fun. Cool. So I'm gonna hard code a direction. I was thinking just now, I'm like, maybe I should have like some kind of stack direction constant and multiply the walk by that, because that would be useful. Push the stack grows up, which is really stupid. So the base pointer, so we want to say, so the base pointer is somewhere, and we have a stack that's ahead of that. So we have a frame, and we want to get all of the things from the stack pointer starting, so starting with the head of the stack. We want the head of the stack on the left. So we'll say, and the stack pointer grows after we push. So the first thing we want to do is, so while SP is greater than BP. So we want to grab all this stuff off of the base pointer. We want to say Xlinks, welcome. How's it going? We're building a stack frame visualizer again, but a better one than last time, so that I can work out what the hell's going on with my function calls, because it's just gotten a little bit silly. It's gotten a little bit strange. And then we have an array called stack. Perfect. Okay, so while this is bigger, we're gonna read something from memory. We're gonna read a whole word. Not wasm ASM, just wasm mod, read, and this might actually just be called read memory. It is. Read memory, yeah, which reads an entire word. We don't have read byte bound because I've never needed it, which is fun, which is kind of fun. Actually, wait, no, maybe I did. I think read memory. Maybe I never used this. Maybe I literally never did that. This dot vm dot read memory. Sure, we'll do it like this. And then we'll say this frame.stack.push v, and then sp minus equals 2. So we're walking backwards down the stack. And once we're done with that, we're gonna say this.frames.push this frame. And then we're just gonna return. We're just gonna calculate one frame. Now, we're also going to do this every time a register updates, which is really, really silly, but that's okay. That is okay. That's weird. What's going on here? PC 0. PC should be a 2. Why isn't the PC in the right place? Because there's an error before we get there. Is there? No? Hello? What did I break? That's weird. That's really weird. Because if I do this now, what the hell? How did I break this so badly? What did I do? Oh, reset doesn't work. Hold on. So I just need to reload and go. Okay, that makes more sense. Cool, there we go. Okay, no panic, crisis averted. So after we do this jump, we're gonna see a frame, and we see a bunch of garbage on the stack, and that's actually okay, because this is, why does this happen? Why does this happen? Why do we have a, oh, because, yeah, so we push stuff to the stack. So we actually have like a leading 0. And that makes sense, because what's the first thing we read? It's SP. So what we actually want to say is, while we want to say SP, we'll just start by subtracting 2 from the stack pointer, right? So Now if we tick through, so we push a couple of things to the stack. This is our return base pointer, I think. So stuff gets pushed. This is good. We're setting up a function call. This is our return address. Oh no, it isn't. Sorry, hold on. Wait, stack SP. Yeah, it is. It is. Push BPSP. PC. Push the program counter. Did we lose our jump? Tom Marks talks crashes. Yeah, this feels a little bit like what this stream's become with the trials and tribulations of the last couple of weeks. How did I break reload? That's weird. I wouldn't have thought hitting reset would break like that. So we jump to here. We push the program counter. We push the and here. Swap. Huh. Did I lose a jump? This is a function call setup, right? But we never actually... Did I delete something really important? Hold on. That would be really funny if I deleted the actual jump. Because I did delete something right next to it. Pop, swap, push. Yeah, I deleted... Hold on. There, I deleted a really important part of the code that actually jumps to the function we're trying to call. So now if I test, it'll be fine, right? Literally all our tests passed. Okay, well that's good to know. I'm looking at this and I'm going crazy. This doesn't make any sense. I cannot... That's really good. That's good news. That's really good news. I'm so happy. I'm so happy with that. So now let's go back into my weird jank code and let's get rid of... I put in this weird hard... this one. Let's see if it still works after that. Yeah, okay. So I can juggle... my temporaries well. Now I now have a stack visualizer. Yeah, true, right? This is never going to be a bad thing. It's a little bit jank. It needs to be a little bit smarter. It needs to pull out the program counter, the kind of return information, because I don't want to visualize that. That should just be magic. Or maybe it can be part of this like preamble where I say the base pointer. But yeah, that is cool and useful. And once I give it a proper UI, mwah, beautiful, beautiful. Oh, man, I'm actually a little bit pressed for time this morning. I really want to tackle the binary operation thing because that's really annoying. Yesterday, 2 days ago, a very helpful person pointed out that I was doing binary operations wrong. So I want to just see if I can quickly write a test for this. We're going to copy this test because this is a good place to start. So what I was doing was, it was right associating wrong, right? So I was doing I was doing b times 2 plus a, right? And I was working out 2 plus a first, basically. So if I test this right now, this will be fine. Lang. Right, this has no problem. But what I actually want to do is say expected, let's say, so we should get b op, no, sorry, so we should have this. This is the left association, right? We should have b expression left, right. So it should be b times 2. So the left should be this, yeah, this whole op. So b to bin op multiply sim a. This is what we expect. Expression found string. Yep, because we're not comparing to a string anymore. That's all good. Op expression That also makes sense. Let's just put a C in here because that's easier, because we have a little helper for this. And that needs a semicolon. Beautiful. Okay, so now this will fail. And this fails because, as we can see, we expect on the left an operator of an operator, but on the right we have an operator like it's right associating instead of left associating. So that's cool. So this is good. So we have a test that fails. And let's see. We have our precedence climb. Now, one of the problems could be that our multiplication precedence is just not set correctly. So we could try changing that. AST bin, right? We have our precedence. What if I make this lower than that? That still fails. Does it fail for the same reason? Yes. So that's good. So that's good to know at least. So what happens when we precedence climb? Bin op input. Yeah, cool. So we get a binary operation. Is this because of how we're doing this tail? Like if we try and we get an expression. No, this is okay, because we just get like a variable, right? We don't do any of the binary operation stuff until here. So we see B, and then we precedence claim, and we should see the multiply. So the expression precedence starts at, it should start at 0, right? Climb recursive, input state, rest, state. We could not be resetting, no, but it should start at 0. It should start at 0, I would think, right? State. Where does state come from? Where does tokenized lex state? Tokenized state, language. Maybe just language. Here it is, state. Expression precedence, so it should start at 0. It should start at 0. And, you know, like, because this is so tightly scoped, we're pretty confident that this is starting at 0. This is the first thing we've done. So the first thing we've seen, climb recursive. So the operator precedence of multiplication is indeed bigger than 0. So that's good. That's good. That is good. Now we try and get the right-hand side. And the right-hand side is going to take this. So when we look at the right-hand side, we're going to get a variable. The multiplication has a precedence of 3. So 3, right? But when we call expression, we haven't updated the state. So what we probably need to do is say s0.expr precedence equals op.get precedence. Okay. That still fails for the same reason. No, it doesn't. This fails for a very different reason. This has now dropped off part of the thing. That's funny. Because basically what's going to happen here is we call this recursively, and so we're just going to go through, we're going to grab the whole thing to the right. Okay. So this algorithm maybe isn't as bulletproof as I thought. Unfortunately, I'm going to have to call it there. I'm going to have to really quickly raid someone and get ready. I am gonna be teaching in a little bit. So thank you everyone who came and hung out for the shorter stream this morning. Oh, hold on. Bobius might have it. 1 + 1. Huh. Left associative. Yeah, that's a good point. So what if I make these more spaced out? So what if I go 3, 5, one. Still fails, but B, C. So it's still doing the add first. But that's an interesting thought. But yeah, no, I do unfortunately have to head off. We're going to quickly raid someone. Hopefully someone's doing something fun that we can find quite quickly. Shipping. Yeah, sorry it was a shorter stream. No, Bobius, that's an interesting point. We should maybe think of it. Let's go look at some retro FPS development in Godot. We're going to do this raid really quickly, and then I'm going to have to bounce very suddenly. Sorry. Thank you so much, everyone who's been tuning in, chipping away at these little problems. And let's go show Jitspo some love. All right, see you next time. Bye.